event. If you want more information about the Institute of World Culture, you go to our website, worldculture.org. Yes. And we have a newsletter, and you can sign up, put your email here if you would like to receive that newsletter. Today's program is the third of a series. It's New Visions of the Vastitude is the overarching theme. So we started out with Eyes on Mars, then we went Eyes on the Earth, and then today, Eyes on the Cosmos. Eyes on the James Webb Space Telescope. So we're definitely looking forward to this, and this is interesting to look at that in terms of the theme for the Institute for the year, which is opening doors through nonviolence and magnanimity. And when you think of the vastitude of the cosmos, you can think of magnanimity indeed. We will be pursuing a number of aims of the Institute, but aim 6 seems particularly relevant, which is to promote forums for fearless inquiry and constructive dialogue concerning the frontiers of science, the therapeutics of self-transformation, and the societies of the future. Now, since we're streaming live, questions out till the end?
If you answer them.
Yeah. So we'll ask.
But I'll say, if somebody has a big question, just go ahead and ask it, or maybe a contribution that you may know something about what we're talking about. So it's just a hybrid model.
Yeah. So unless you have a big question, hold until the end, which is helpful for because we're streaming, and then you have to have the question repeated, and it gets a little awkward. And then the people that are watching on YouTube can ask a question in the section dedicated to that, the chat. Our speaker tonight, Russ Lewin, is usually sitting over there running the live stream. And that pretty much all the technology, our humble attempt here, has been set up and kept going by Russ Lewin. He's our tech advisor. He's been a member of the Institute since its founding. He has been its president in the past. He has had a number of careers, but the last one was at Santa Barbara Middle School, where he taught math, physics, various electives, including film production. Now, I think it was 2019, he presented on a grand tour of the solar system. So, but he's very eclectic, Last year on American Symbols, he did a seminar on AI, the emerging revolution. Not surprisingly, he did one on Hellenistic civilization, math and science, and and one I particularly loved on John Wesley Powell, which he called Starlight in the Stone Temple of the West. And he also did a forum on the photography of Ansel Adams. And he is a first-rate wildlife photographer, among other things. I mean, the guy's a Renaissance man. So let's give him a big hand. Thank you.
Thank you, Robert. All right, let's jump in. Let's see here. Yep. Well, welcome everybody, and I hope you're excited as I am about the Webb Space Telescope. And really, it just goes to show what can be done in terms of the greater good when people work for something beyond themselves. The Webb Space Telescope has been in production for decades, cost $10 billion to make it. Americans, Canadians, Europeans, people from Asia, people from everywhere worked on it. And today we get to celebrate the fruits of their labors. So the Webb is a telescope that is 100 times more sensitive than the Hubble Space Telescope, 100 times, and is reaching back to the origins of the solar system. Now, it's named after James Webb, and he was the administrator during the Apollo era of NASA, so all of those big moon missions were run by Jim Webb. It's like a fantastic boost to the organization. So you're going to need, I have to give you a little bit of training today in order to, get you out into space just like any astronaut. And the idea is you have to be curious. And Einstein said, I have no special talents. I am only passionately curious. So if we think about that, do you sometimes think, how big is the universe? What is it? Where do we come from? What's the nature of things? How can I enhance my perceptions in relation to all this? And it seems like if we have a genuine curiosity where we not doubt things, but wonder big, really, really big. So I have a special piece of technology. So as everybody walked into the room today, I took a picture of everybody, you couldn't tell, and this software morphs it together. And this is what we all look like as one person. That's what wonder looks like. And we all started there. We all started at that point where the universe was purely wondrous and everything was like seeing it for the first time. So if we could sort of like clear our minds and take that perspective. Now, here are the science goals. These are the primary science goals of the mission. We wonder. It's our nature. How did we get here? Are we alone in the universe? And how does the universe work? Now, I think those are relatively modest goals. How does the universe work? In other words, scientists have a sense of humor. They're saying, well, we want to know everything about everything. And it's just a really fresh perspective that we can all take. Now, how many people in the room think there's a center to the universe? A center to the universe, a central point around which everything revolves.
Of course, there has to be.
Has to be, okay. And how many people think, no, there's no center? How many think, well, could be both? Well, the answer to that question, according to the great astronomers in the world, is we don't know that there is a center. We don't know that the universe is linear, that it goes out in a straight line. It could be curved. It could have dimensions to it. It could be a bubble in space, like amidst other bubbles. We don't know. So here's the view. This is like a mandala, but what it is a picture of the universe with the Earth in the center of it, because that's our perspective. Right. When we look out, you'll see here, you've got the solar system, followed by so sort of like space, and then you've got galaxies, and then you get into the origins of the universe when it was like a cosmic soup. And no matter what direction you look, you'll basically see the same levels or dimensions of the universe. It's not in just one particular direction. So we have to really reformulate our idea of looking back towards the center, because we're sort of in the middle of it all. And that's sometimes very difficult to get our minds around, because we typically see the universe like this, you know, where we're saying, well, it's sort of like a channel, and we look back through it. Now, one way to look at this is back through, we're looking back through here. So the very first origins of the universe here, in the first trillionth of a second, much of the universe was established. It starts off as a pure mix of energy and space and material. It's truly one thing. And then there's like a radical period of the establishment of the constituents of the universe, the subatomic particles, which then form and make protons. And these protons are in this sort of galactic soup. And nothing really happens for a period of time that we can detect until there's this dark period of the universe. This is a soup. And you can't see any of that. It's not until about 380,000 years into it that we can actually start to see what's there. And we're hoping to look back to about here with the Webb. We're hoping to see that far. The Hubble can go to about here. So we're looking for the original galaxies, the original stars, and they have already started to see them. So when we're looking here, we're saying, okay, if we take this curiosity, what we see with our eyes isn't the whole picture. In fact, the Webb takes pictures that are entirely invisible to the naked eye. It photographs, it assesses in the infrared spectrum, which we cannot see. So what it does is take these images and it actually assigns colors to them so that we can see them, but they're invisible to the naked eye. We can't see in infrared. So what I want to do is, rather than make you wait an hour to see the really great stuff, I'd like to just start by showing you 14 of the highlights that have come down from the Hubble. So here's the first one, and it's called the Pillars of Creation. You may have seen pictures of this from the Hubble, but not like this. So this is a great time of year to look up in the sky. So if you go outside, you'll see Orion. It's an easy constellation to see in the sky. And if you sort of look towards the belt, there's a little nebula called the Eagle Nebula. And embedded in the Eagle Nebula are the pillars of creation. And what you're seeing are stars being born. So if we look here, for example, or we look here or here, we're seeing actual creation zones of brand new stars from this cosmic dust. In fact, all of these stars in here, all over the place, are in formation. We're going to talk about all these things as we go on, but I just want to give you that highlight. Next, this is the Cartwheel Galaxy. And this is the result of two giant galaxies that collided together a couple of 100 million years ago. And there are spokes. These are like spokes radiating out. Imagine like if you threw a stone in a pond here, it would ripple outward. And that's exactly what's happening on this grand galactic scale. So we're able to, assess what the dynamic is there. So that's the Cartwheel Galaxy. This is an actual photograph that has been taken in infrared called the Wolf-Rayet 140. And what is essentially is two stars. So they're orbiting around each other. One's like this, and then the other comes around like this. And they're late-stage stars, so they're ejecting material at a massive rate. They're about 25 times the mass of the sun, and they're ejecting these carbon-rich materials into space, and as they whip around each other, they're creating these waves, and the waves have created this pattern. Wolf Rayets are, they're very hot stars, but they're relatively rare. Next is the Carina Nebula. And this is sometimes referred to as the cosmic cliffs because of the contouring that we're able to see. This is about 7,600 light years away. That means it's really, really, really close. And it's something we've never seen in this context before because this is an infrared photograph that can actually see through the dust and the material and see what's happening in there. It's a stellar nursery. Now, it's estimated that in our universe, 400 million stars are born every day, which means there's one every 1/5,000th of a second being born. So if I say beep, 5,000 stars were born. What can I say? It's a big place. Lots of things are happening.
In the universe or in the galaxy?
In the universe, yeah. Okay, so we're going to talk more about all these things, as I said. This is the Tarantula Nebula. Somebody thought this looked like a tarantula. Frankly, I think they need to take up golf, but they're calling it the Tarantula Nebula. There's about 500,000 stars in there. And what's particularly compelling about this, because this is taken with the infrared camera, it sees through the dust, and at the center of it is this really, really bright starburst region. So when they find areas that exemplify hyperactivity on a cosmic scale, that's worthy of study because they really need to know, well, why is it like that? And we'll study that. Next is the Phantom Galaxy. And this galaxy is referred to as a grand design galaxy. Grand design. There's not patchy. It's got like a really careful geometry or architecture to it. So it's got this definition. And because of the infrared cameras, we can see right to the core of it. But you can see the well-defined rings all around it, spinning out very, very carefully. And normally it would just be a giant haze. So the Hubble is able to detect these things. Jupiter, as never seen before. So they decided, let's just see what happens when we take a picture of a planet. And now, it's hard to detect the rings of Jupiter because they're 1,000,000 times fainter than the planet itself. The planet's intense, and it reflects a lot of light. But in infrared, they were able to pick up clearly defined rings here. And then there's another one coming out in this direction. In addition, you can see auroras, just like we have on Earth, on Jupiter. You can see the big red spot. It's not red because it reflects so much light. It turns out to be kind of whitish. And they're able to, start to study the dynamics of Jupiter. Jupiter's not understood at all. It doesn't really have a hard surface. It's some kind of hypermaterial that is just faintly being understood. A lot of mysteries there. So this was a big celebration to see how well it could do. Anybody want to take a guess at that one? That's right, Neptune. That's a picture of Neptune in infrared, but you'll notice here, that's Triton. And Triton is a large moon. It's in retrograde motion, so it goes in the opposite direction as the rest of the moons. But it has actual ice geysers on it, ice geysers. And the thought is it was probably captured from the Kuiper belt gravitationally by Neptune. There's a close-up of it. And what's important about this is that Neptune is highly reflective of light. So you might say, well, that's not really, an in-focus photograph, but it's kind of photographing the dynamics of it. This is a near infrared. So there's two types of camera, near infrared and mid infrared, and they capture different things altogether. Plus they have filters. Now, the patches here and here are, they think, high altitude methane ice clouds. And along the equator in here, you see some thin lines there, but they think it could be storms that constantly circulate around the planet at very, very high speed, but in the middle of the planet, near the equator. And on the southern pole, for the first time, they have found high altitude clouds that have formed a kind of vortex, and that's here. They don't know exactly what these things mean. These are discoveries that are being made. And then, of course, the rings, which are always a spectacular area of study, have come out exceptionally well. And the scientists are ecstatic that they're able to get these kinds of images of our own solar system. And they're just started. These were like casual snapshots just to see how it would work, and it worked really, really well. Another highlight, this is the Southern Ring Nebula. And it's about a half a light year across. But as we'll find soon, it's like sometimes they call it a planetary nebula. So as stars go through their cycle, like our sun, they turn into red giants, and then they start to sort of shed all this material. And then it turns into a white dwarf star. And so the question is, well, how does it get this elaborate pattern? And what we'll soon find is that through the infrared photography, they were able to find that there's two stars in there, not one. There's two, and that was never known before. This is another big discovery. Next, these are side-by-side galaxies. One's a spiral. The other is, I think, probably elliptical. But what's interesting is Einstein explained to us in, I think, 1916 that gravity is different than we think it is. That gravity, or mass, warps the space-time continuum. So space curves. And if it curves, the question became, will light curve with it? And the answer is yes, it will curve with it. So what you're seeing here is a very, very ancient and distant galaxy that's being bent around the foreground galaxy. So you're looking right here. That's a galaxy that we weren't able to previously see that's being bent around another galaxy. It's called gravitational lensing. So gravity itself causes a lens by which we can study the deeper parts of the universe. So to illustrate that more, just kind of a simple example of how space is different than we think it is. And this is just, a very superficial model, but all the studies thus far have shown that Einstein was absolutely correct in his assessments. If we look at a model of it here, you'll notice this would be the distant object, and it sheds its light thus. But the mass of these objects in here distorts space-time enough that it gets bent around and becomes visible to the observer here. That is quite remarkable. And there are a number of examples of that. They're referred to as Einstein rings. Next. This is also the pillars of creation. We saw that earlier. This is in mid-infrared light. So what it emphasizes sort of like a different dimension. And so it picks up the kind of cloud contouring and texturing of these nebulas. You could still see, the areas where stars are being created, all through here and here and here. There are millions of them in there. And it's a different way of looking at it, a different way of seeing it. So they look at it through different eyes. It's a little bit like the six blind men and the elephant, using different tools to see it. Next, these are merging galaxies. It turns out that the merger of galaxies is not all that uncommon. And in fact, the Milky Way will merge with the Andromeda galaxy, but it will be several million years or more before that actually occurs. But they do occur out in the universe. And this one's only 270 million light years away. Now, you could say, how's that close? Well, we're talking about a universe that's about 14 billion years old, so the light has been traveling that far. This is very close in relation to 14 billion. Massive starburst in the center of it, 20 times the rate of the Milky Way. And a really good candidate for studying the formation of black holes. Next. Now this is the deep field view. So what they do, imagine a grain of sand, and you put it on your finger, and you hold the grain of sand outstretched entirely. That's size in relation to the sky. And then you hold the telescope on that point for about 12 and a half hours. And this is what they saw. I mean, I don't have words for this because it's just too spectacular and, if I may say, cosmic. Cosmic in the sense that you're seeing galaxies, and this is a galaxy here that has been gravitationally lensed, as well as these particles are these here and here and here. In other words, it's everywhere. It's able now to pick up not just, the millions of galaxies in the so-called foreground. It's pulling out the original galaxies from the background, hence the term deep field. Let's see, go back here. This is supposed to go. Oh, I know what I'll do. So here we'll dive into it. And if you scan, virtually every dot there is a galaxy. These sort of bright, starry little guys in there are foreground stars. Everything else is a different galaxy, different age, different era of the universe. But because they're so distant and they sent light that took billions of years to reach us, we can see them how they once were and in their original state. And now, I gotta say, you can say, well, galaxy, like the Milky Way, there can't be that many of them, like 10 or 20 or, well, apparently they think more than 2 trillion of them, 2 trillion. Basically, if you took all the grains of sand on all the beaches of the world, there are more galaxies than that. Galaxies. I just have to be quiet now for a period of time. Really, it's like so gripping. like if you realize what they're saying to us. Whoa. Now, we also have galaxy clusters. So these guys here are all little galaxies that are relatively close and form a kind of galaxy ecosystem. That the gravitational forces are so intense that they can pull material from each other and form stars in the middle. And all kinds of other things. So this is the whole deep dynamic that takes place, plus all kinds of gravitationally lensed galaxies in the background. So there's a lot of work that they have to do on that. Now, here, and this is quite fascinating, you know, people do studies on all these things. So we're getting these pictures back, and then, you know, university teams and so forth get together and try to figure out, you know, what these things are. But there are, I think, 3 boxes here. There's 1, 2, 3 that connect over here. And what this shows is, well, not only completely new galaxies, but the resolution on the Webb is good enough to show that there's actually 2 of them there. So first, we were never able to see anything like this before. Now we can see it and even distinguish differences in that little galactic structure. Now, lest we think that only geniuses can work on this, this is a team, a Canadian team. You gotta love Canada. And they did a study on one little part of the deep field. And I'll show you that and then come back to this. So this is what they actually studied. And it's a little tiny structure right there, which is amplified by a structure right there, that little tiny box. This is what the Hubble could see. And then they were able to resolve that into that and discover a globular cluster, which are also relatively rare. I think there's about 150 of them in the Milky Way. And I think for me, their faces say it all. I mean, this is people who love science. Sometimes they say, well, you know, or you go to a science or a math conference, they laugh at the wrong time. Actually, they laugh because they sort of get what the average person doesn't. They see in between the lines. And so they made this, this discovery, and there are lots and lots and lots of teams who are working on everything that they're discovering, and then you can make suggestions and get time on the web to actually do a project. And so they've got all these great things lined up. And one of the researchers says, the Webb was built to find the first stars and galaxies, to help us understand the origins of complexity in the universe, such as the chemical elements and the building blocks of life. So, you know, big science. Stephan's quintet. I know you're saying there's only 4 of them there, but let's see, different color. 1, 2, 3, 4, 5. This one here is way in the foreground. So essentially, there's just 4 of them. And the other really amazing thing here we're going to talk about, there's a supermassive black hole right there, highly visible, that we will be able to research and study. So this was actually in a movie, old movie. Anybody remember what movie? It's a Wonderful Life with Jimmy Stewart. At a certain point, he looks up and they can see this. So these telescopes can be able to see this, but not at this level of resolution. All right, now here's the thing. When we look up in the sky, how do we know how far away something is? Just like if there was a little earthquake, how do we know if it was just a little earthquake in the channel or a massive earthquake someplace else. Same with stars. How do we know just if it's bright because it's close or because it's really huge and far away? Say?
Radar, seismography.
Okay, that's a possibility. There's all kinds of ways to do it. But let me give you an illustration first, because you can't really see it with your eye. So this is an example. Let me get this up here. Yeah, this is an example of depth perception. Sorry. Sorry. Oh, I have to switch. Hang on. To get films, I have to go to 2. Okay, so I'm going to 2. And I'm going to restart that one. Okay. So she's juggling, but how do we know how high, what ball's high and what ball's low? I mean, occasionally you can see it, but by and large you can't. That's like looking up in the sky. Depth perception. You need a frame of reference. Without a frame of reference, if you're in a dark room and there's a light and you don't have a frame of reference, you can't tell how big it is and where it is or how far away it is. We take all that for granted. And we have stereoscopic vision, but that doesn't help us when we're looking up into the sky. So, let me get back to camera 3. So that's why we have to celebrate Henrietta Swan Leavitt, who was an associate of Edwin Hubble. But in 1900, women didn't get a lot of credit. They just didn't. For the most part, still don't. But she actually unlocked the way that we're able to find how far away things are in the universe. Now, she worked at Harvard in 1890 as a calculator, and they called them computers. They were human beings, and they called them computers. They would calculate things. And her job was to measure and observe Cepheid variable stars. And so she measured over 200 of them and observed them and found that this was a particular kind of star that blinks. And if something blinks really fast and it's a Cepheid, then that means it's dim. If it pulses slowly and it's a Cepheid, it's a very bright star. So it's just sort of like the wattage of a light bulb could then be assigned to a particular type of blinking star. Once they had that, they actually had a way to measure the distance to things. So if you look out in Andromeda and you can see various Cepheids, she was able to assign the luminosity due to the rate of blinking to how far away it was. This was a key that opened the universe, and we could all of a sudden establish that, in fact, there are galaxies, when before we had no sure way of knowing that. It could just be part of the Milky Way. How do we know? And then all of a sudden, one galaxy, another, and another, and another. So this was such a breakthrough, and has actually been made basically into a standard. They call it the standard candle. So you can measure a Cepheid, take the luminosity, compare it to the period of variability, and you could tell how far away it is. So, Henrietta Leavitt.
If you're just taking snap photographs, how do you know how rapidly something's...
Yeah, that's a good point. It doesn't, you have to like take a whole bunch of photographs over days and days to get the pattern. All right, so this really, really opened things up. And then the next thing that was discovered, equally amazing, was something called Hubble's law. I didn't draw this. I'm a much worse drawer than this. So this shows when they started measuring these various galaxies and how far away, they realized that they're actually moving rapidly. And so galaxies that are near are moving away from us more slowly than galaxies that are far away. That the entire universe that we live in is expanding in all directions, like a balloon being blown up. And this is referred to as Hubble's law, and is used to calculate the rate of expansion. Some of the galaxies very far away are like a third the speed of light at the rate at which they're expanding, like rapidly. The question is, how? How could this be? Why? So say I'm a baseball pitcher, because it's World Series time, and I throw a pitch, it leaves my hand at 100 miles per hour. When it reaches the plate, it's going 200 miles an hour. How? You know, that defies the laws of physics. Shouldn't it be slowing down because of friction and gravity and so forth? So that begs the question, is there another force in the universe? Which is now being referred to as dark energy. So here we have a sort of a model of the universe and how it's expansive, sort of like a bugle model. And so the universe is expanding, and the more distant it is, the faster, but it's uniform in all directions. This has implications on how we're going to photograph things and why we have to photograph them in infrared. So let me explain that. So if, for instance, let me switch the camera here. Yeah. All right, so this car is standing still. So you'll notice the wavelengths here and here are the same. But down here, the car is moving in this direction. These wavelengths are compressed, and these wavelengths are elongated. So this Doppler effect, I have a visual or a video here, so let me go back to 2. And you're not getting any sound. Okay, I'll let's see. As a car comes towards you, you know, it goes by you. The pitch changes because the wavelengths change. And the same thing happens with light. So as the universe expanded, stars that are moving outward have elongated wavelengths, shifting them towards the red end of the spectrum. So red light has a longer wavelength than blue light. It's the same speed because it's light, but it changes the color of it. And if something's moving towards us, then it compresses the wavelengths, and that pushes it up into the blue end of the spectrum. So it works the same way as sound. And this is a joke which says, this is Edwin Hubble's car, you know, and he's the expanding universe. Objects in the mirror are bluer than they seem. So objects moving towards the mirror are compressed a little bit towards the blue end of the spectrum. So there you have the funny joke. Now, how did we discover infrared to begin with? William Herschel may not be his best picture, but brilliant, beyond brilliant scientist. He discovered Uranus. Anyway, at 1800, he was like wondering about things. He's a contrarian, and he said, well, is it possible that each color of light coming through a prism has a different temperature? I should measure that. He did, and he's like, whoa, they are different temperatures. And then he measured to the other side of red and said, well, It's got a different temperature that's higher still, but we can't see it. Is it possible that there's forms of light we can't see? The discovery of not only infrared, but the electromagnetic spectrum. So now, he was an interesting story. He was a German immigrant, moved to England, was a band leader, kind of musician, and decided that he, at 34, should be more interested in astronomy. So he got a book, and he got a telescope, and then a few years later discovered Uranus. Later became the king's astronomer. So he's just one of the most interesting scientists, and I would urge everybody, to sort of run out and study him. So the implications here are that the color of what we see, visible light, does not tell the whole story. There's something above that, infrared, and something below that, ultraviolet. So the electromagnetic spectrum, this is infrared over here. And this is the visible. And this is where the Webb is working, right in here. And just to correlate it with wavelengths, you'll notice that colors have wavelengths, and the longer the wavelength, the more it tends towards the red end of the spectrum. So that's just sort of an interesting thing, and this is where infrared is, but there's microwave and radio waves, and when you go in to take an X-ray, we're all working here on the electromagnetic spectrum. All right, so we have cameras now that can easily take pictures in infrared. In fact, one of the leading companies, FLIR, F-L-I-R, is right in Galita, and they're the ones that are making a lot of this stuff. So if you see something in terms of more like heat, it gives you a completely different signature than just visible. So here's the punchline. We could see through things. Okay, so this is visible here. And we can't see anything, but in the infrared side of it, we can see right through it. So if this is all debris from various nebulas and all kinds of cosmic dust and so forth, with really good cameras that are floating up in space, cooled, to almost 0 Kelvin, we can see through obstacles. And this is the big effort of the Webb to make that happen.
Hey, Ross?
Yeah.
It's kind of interesting that his lenses are the opposite, aren't they? Visible light can see through the lens, but infrared gets blocked.
Because it reflects. So the glass is reflecting, yeah. Yeah, there's all kinds of little tricky phenomena in there. But to be able to see through something, if you actually get an infrared camera and take pictures, I gotta say, it takes you a while to kind of get your mind around it.
Russ, another question.
Yeah.
So isn't it true that infrared is measuring heat content as well? That's what it's detecting is the
Mostly,
temperature?
mostly,
Okay.
mostly, yeah.
But you mentioned those two different types.
Yeah, so there's different frequencies of infrared. So the spectrum is like from sort of a low frequency to a high frequency in its own category. And then they take pictures at different frequencies, and it draws out different elements of whatever they're observing.
But we don't think of heat as part of the electromagnetic spectrum.
We don't think of it that way. It's not just heat, though. The scientists explain heat's a way to explain it. It has more to do with wavelength.
Something we can touch.
We tend to think of it too sensually, in terms of like what we can feel and sense, but it definitely transcends that. 5G is sort of near microwave. So if you're near a cell tower, don't go up and stand next to it. It's really bad. All right. Now, so the implication of all this buildup is the whole cosmos has shifted to the red end of the spectrum due to the expansion. And so if you want to see most of what's there, you have to try to view it in the infrared side of the spectrum. So something like, let's see, yeah, so this is the Webb, and you'll notice it comes all the way down here, and that's infrared. Hubble had an infrared detector, but it wasn't nearly as strong, so it would only come to about there. So we have to take advantage of that, and to do it, we built this amazing telescope, the Webb Space Telescope. Now, it has to be in space because it has to be extremely cold in order for it to detect properly. So it's only, they actually cool, it's really cold out there to begin with, and they're cooling it even further so that they can stabilize the telescope. And when they do, they start to get pictures like this. This is visible, and that's in infrared. You see right through it. And look at the stars and galaxies and dynamics of everything in that structure, when previously we'd be just looking at the husk of it. It's a little bit like a human being, you know, you appear a certain way and so forth. But inside there are stars. There's all these stars in human beings. And when we perceive stars in human beings, that's what makes us truly, you know, interested in them. So similarly, space is structured that way. Just to highlight again, this is the Webb, and this is the range. So we were talking earlier about, well, what about, why isn't it just one thing? There are actually sections of the infrared spectrum, sorry. There are sections to it. And the Webb does most of its work here, and some of it here and here. If it's a crisp photograph, it's there. If it's more like emphasizing the clouds, that's mid-infrared, out in there. This is going to take us all the way back to the original galaxies, just using what we've learned so far today. So this wonderful telescope, which floats in space. And so what you're seeing here, and this is the scope right here. The sun is back here. It always has to be pointed away from the sun, so sun rays. And to protect it, it's got this sun shield. And the sun shield is about the size of a tennis court, and several layers of reflective material that basically keep the sun from touching it at all. That keeps it very, very, very cool. So the amount of engineering involved to make sure that no matter where the scope is, it's pointed away from the sun is significant. It's got various instruments on board, basically not all that difficult to understand. It's got this incredible mirror and then 4 primary science tools. Near-infrared camera, mid-infrared, spectroscope, and another one that's sort of a mix of them. Integrated science module. And now, the mirror itself, I mean, oh my gosh, it's, you know, 6.6 meters across, but they made like 18 hexagonal miniature lenses that work together as one. The backing is beryllium, because it's light and it's strong. And then it's coated with a layer of gold, a molecular layer of gold, because that reflects infrared the best. And all of these can be used individually or collectively. When the light comes in, they've got this system of, they call it micro shutters. So the light goes through, there's 248,000 little micro shutters, and you can open or close them and observe as many as 100 objects at a time, depending on the micro array. Now that's engineering. Oh my gosh. And gets really specific information from it. Has to be stabilized. The whole time it's up there, it has to be perfectly still while it's moving. And I mean, boy, these scientists are really something. So you can see it's large. It took them decades to build this and to perfect it. So the area of the mirror is 5 times that of the Hubble. Really, really large. And the question, of course, is, well, how are we going to get this into space? I mean, did you think about how we would put this in a spacecraft? And well, it's big, and this is the light sort of comes in like this, and it bounces out here, gets focused, and then goes into sort of the instrument chamber where it's measured right in here. But how are we going to get all this stuff here into a spacecraft? Well, each thing is very carefully built. It's like really delicate. It costs $10 billion to make this. So they decided, well, we'll make it into these hexagons so that we can like fold the hexagons, at the creases. And now, once we get back out there, we're going to have to reassemble all this stuff. So we're going to wind it up into a little package, send it out, and then while it's floating in space towards its destination, we'll just have all these little tiny robots and things unfolding. 200 steps to unfold the telescope. If any of the 200 steps did not work, the telescope would not work. Big engineering, big engineering. And as you know, it did work. And so they actually have, now the next thing is, well, where will we put this thing? So they put it out at what's called L2. And it's a little Lagrange point. So basically, if you sort of look at it like this, it stays on that line. So as the Earth orbits, it orbits right behind it in the same fashion. And so the Earth will always be shielding the spacecraft from the sun. Now, they're not putting it right on it. It orbits around L2. And then at certain points, where depending on where it is, it can more easily like photograph a planet. Like maybe the planet is like over here or something like that. And so as we come along this way, they could actually take a photograph of it like that. So they have to wait until it's in position. So far, this has worked really, really well. Now, if it needs to be adjusted, or maybe it needs some WD-40 to do something, there is no way to get out there. We do not know how to get out there. The other thing is, the distance from the Earth to the sun is about 93 million miles, but the distance from here to here is about 1 million miles. So this is not to scale. But again, the engineering, remarkable. There's the observing side and the sun-facing side, and the instrumentation has been modeled accordingly. The cold side is minus 388 degrees Fahrenheit, The hot side is 185 degrees Fahrenheit. Oh my gosh. Oh my gosh. You know, it's like a huge 500 plus degree difference. So to model this, they had to make a sunscreen. And they figured out a way to do it with this thin insulating material. And then in between, they have these structures so that there's a minimum touching top-bottom, which disallows conduction. And there's 5 of them, so whatever heat is conducted can easily be dispelled. And they found that it's enough to cut virtually 100% of the heat coming from the sun from reaching the spacecraft. Oh my gosh. And there's a picture of it. And there's the team. So people, you know, are assigned to these teams. They may work 10 years or 15 years just building this structure carefully. And that always seems to be overlooked. We never appreciate the people that do this deep work. And every time they walk in, they have to suit up and go through a clean room because you can't get any dust on it. That could influence the whole thing. And they work tirelessly at this. If you're interested ever in seeing something like this built, you can go to the Jet Propulsion Lab in Pasadena, and you can take tours. I used to take my classes there every year, and every year 2 or 3 would say, oh, that's what I'm doing. I'm going to be a scientist. Because if you don't see a scientist working, why would you want to be one? I mean, you see rock and roll people. Anyway, sometimes it's hard for me to mask my enthusiasm, but okay, so here it is, all packaged up, right here. Look at that. It's like a little origami situation where they had to like mold it up into this little case and then put it into the payload area and launch it. And then once it gets up far enough, it has to like be released into space where it can actually navigate to its destination while it unfolds, Oh, so let me get back to camera 2 and see what we get.
So is it all unfolded now?
Yes, all unfolded, sitting nicely out at L2, observing things in space. I just am so amazed by every aspect of this. I mean, just to get it out there was a big project. All right, let's go back to 3.
You said fold it into a little package. It doesn't look very little.
Well, compared to what it was, you know, it's like so sort of like take a couple of elephants and put them in a Subaru type thing.
So where is it now? Does it have a measurement, a way of measuring where it is?
Yes. So this is the Earth right here. And so it made its way all the way out to this point here, L2. So it's 1 million miles, roughly, from the Earth. And it sort of is in synchronous orbit. So as the Earth moves, the Webb moves with it around the sun.
Did you say it's in the Earth's shadow?
Yes. Yep. That was the design because all the heat from the sun, you know, is going to like disallow infrared photography. How do we shield it? And that's how they do it. It's not 100% of the time, but enough to make a difference. And
Get affected by eclipses and things like that?
yeah, it could be, but beneficially. Yeah. Then, now once they get it out there, you have to communicate with Earth. So it's got, you know, it's got sort of a dish here, and it can send and receive things to Earth. So it sends it over to Goldstone in California. And then it's distributed. Like they send it over. Baltimore, I think, is where the headquarters is, where they process everything. And we can send commands back to it. In other words, we can point it in various ways so that it can actually observe things. Now, I mean, when I go out, you know, I look at, because I was out last night looking at stuff, and it's not that easy to find stuff, honestly. But they're pinpointing things that are so precise and able to hold the telescope there and gather these images. You really have to appreciate how developed these scientists are to be able to do that. And it's not just machines doing it. Okay, so let's get back into some of the pictures. The Carina Nebula. Nebula is a giant cloud of dust and gas in space. Nature has an economy which is perfect. So stars will go through a cycle, and then when they reach a certain point, they'll either explode or sort of like turn into red giants and disintegrate. But all that material gets regathered into nebulas, and then the nebulas become rookeries for new stars. That's how it works. And we don't understand it that well, but this is sort of what it looks like. Now, as I mentioned before, this is in Orion in the Eagle Nebula, and it shows early star formation. Now, what do we mean early star formation? Well, what's unusual about here is that these stars that they're viewing are true baby stars. They're 50,000 to 100,000 years old. It takes millions of years to form a star. We're seeing, you know, just the baby tadpoles come out and grow, protostars, and they're finding that they have jets that are like spewing out gas. And because they're here, when they do close-ups, they can see the background being contoured by the jets of these stars, allowing them to see how strong they are, what direction they point their ejecta. And it's a very, very rare opportunity to observe stellar development. Very rare. And you could only see it on the infrared spectrum. So Hubble came close, but this is, you know, better for sure. Okay, so here we are, and this is in infrared, so you're not seeing all of the debris in front of it, and the hot ionized gas is streaming away. It's like ultraviolet, and it can strip away this sort of cloud material. And the clouds are mostly made out of hydrocarbons. And the jets, the protostellar jets, are sort of like the little gold structures. And each one of these can be specialized, and teams can go in and actually examine it and try to distill, you know, what's the scientific process here. I mean, they say things like, we see examples of structures that honestly we don't even know what they are. Like, what's going on here? The data is so rich. These are, you know, project managers for the team. So, starbirth. And they're sort of protostellar. They're not sort of, they're protostellar. So the gas and the dust and the debris and the carbon and these various materials sort of coalesce, and then they start to spin. And as they spin, they start to compact. And when they compact enough, they reach critical mass, which means they engage in nuclear fusion, which generates light. They think. Do we know all this for sure? No, we don't. What if it's something different? Well, then we have yet to discover it, but that's the working theory.
Is that a photograph or
That's an artist rendition. Yeah. So,
Could we ask a question?
Yeah.
When you see the scene with the brown, and then there was the slide which had kind of the brown pillars going out.
uh-huh.
You used the word compact. What is the source of cohesion? Because, you know, there's that stuff that has been depicted in brown, and then there's, I guess, space. But maybe cohesion's an old-fashioned word, not appropriate to this, but we're just kind of wondering, and you talk about hydrogen and helium, that somehow things compact and then they disappear or whatever.
Yeah.
But I mean, it would be the parallel to what we think of what gravity does. Gravity pushes things together. Or what's happening there?
Yeah, it's gravity. You know, as we mentioned earlier, gravity warps the space-time continuum. And they've done experiments on the International Space Station where they'll take balls of different masses and drop them in space besides the space station. And the idea is, so what are they going to do? Are they going to drift off into space? No. They form their own little gravitational system. If the two objects are the same mass, they orbit around each other. If one's much more massive than the other, it orbits around it. Even on this micro scale, they've established that that's a law of nature. So it's gravity, but a new kind of gravity. It's a little more sophisticated than, you know, when I was in Mr. Harris's class in the 3rd grade. Again, do we know all this for sure? Well, no. You know, this is a best guess, really. All right. So now, I think this is a little film, short film. So let me switch over to camera 2. Yeah. Okay. So this is, I know what I could do. Bear with me for a moment.
Begins in dark, dense clouds.
Okay, I'll go back and try it again.
Newborn stars are found within brilliant, colorful nebulae. However, star formation begins in dark, dense clouds. Within one vast dark cloud, gravity collapses thousands of individual dense clumps. The core of a massive dense clump will compress and heat until it forms a protostar. A protostar grows as a disk of gas and dust accretes onto it, and some of the accreting material is ejected along twin opposing jets. While the star finishes its formation, planets build up within the surrounding disk. A few 100 million years later, the new solar system has assembled. Stars and planets form together at billions of sites across our galaxy.
So that gives you a little bit of an idea of how they think the stars are emerging from these nebula. Now, this next image here, let me switch over. Let's see, go to camera 3. Okay. All right, this is an important diagram. So when stars form in nebula, say here, this is what we're looking at. So the pillars of creation, or the Carina Nebula, is generating all of these stars. Now, If it's sufficiently massive, it goes in this direction. If it's not so massive, like our sun is not a massive star, it's going to go in this direction, over here. So a massive star is going to head over towards becoming a red supergiant, eventually will supernova, at what point it becomes either a black hole or a neutron star, or possibly just debris and goes back into making a nebula where more stars are made. So that's that loop there. If it's a smaller star, like our sun, it goes in this direction. It becomes a sun-like star, a red giant, not a super red giant, but a red giant, a planetary nebula. We've seen at least one of those. And then it will become a white dwarf. And the material that's left over goes back into star-forming nebulas. Now, what's also interesting about this is that these materials, when they take these various forms, whether it be a massive star or a red giant, there's nuclear fusion going on in the core. And that's actually causing the elements to form. So the elements on the periodic table were generated in star nuclei. So you think, well, think about this. We all have blood coursing through our bodies, and we have hemoglobin, and hemoglobin, attracts oxygen. Well, what's hemoglobin made out of? Well, it's like iron. Where'd iron come from? Stars. Stars. The material that makes up not just our bodies, but the earth, all those materials come from stars. This is how it occurs. These are your ancestors. And it's very difficult, to wrap one's mind around this. But the economy of nature is so elegant and deliberate, and it may take billions of years to unfold, but an undeniable beauty and elegance.
Hey, Russ,
Yeah.
how does a single star's material that becomes a nebula become a nursery for many stars?
Yeah. Well, these are large, so these structures are light years across, and the material is relatively dense, so it's not like a cloud like we'd think of it. It's dense, and it has, hydrocarbons in it, and all kinds of things that were generated previously in other stars. And they actually, some are more dense than others, and they're drawn together gravitationally, and then more draws to it and more, and then at a certain point it has enough mass to coalesce and eventually generate nuclear fusion.
So you mean that the nebula is not just the material of one exploded star, so to speak. It actually accumulates mass from other parts of the...
Yeah, yes. These are massive structures. So like the Carina Nebula, it's like 12 light years high. Now, let's take a second with that, because, oh yeah, sure, 12 light years. Light travels from the sun to the earth in 8 minutes. That's 8 light minutes. It's almost incomprehensible to think of how far light would travel in a year. So it's like, 6 trillion miles or 10 trillion kilometers in a year. And then if it's 12, it's like we're talking about something 12 trillion miles high. What can you say? I mean, surrender, I think, is the answer, because these structures are so large, and the material is often very, very dense. And it could be material not just from one star, but many, many stars contributing to it and generating yet new stars. And so the term star rookery is, quaint, but, it seems like there's more to it. Yes, sir?
In the last series, you showed star, which is creating the star, that the planets that are rotating around it, so it's creating a solar system.
It can. It can.
That's the speculation anyway.
It can, absolutely.
But are there other ways that planets are
Yeah.
part of a system? Like
Yeah.
comet can become part of a system?
Yes. Yeah, I mean, there could be a star that can gravitationally capture other bodies. You know, like Neptune, for example, probably captured Triton and it became a moon. So it could work that way too. All right, Southern Ring Nebula. Beautiful, beautiful, beautiful.
But you did explain the black hole over there. I want to know the significance of the black hole of the last year.
Black hole. Okay. So black holes, we think. We don't know this. We think, and this is why it's so exciting to study these structures. Maybe we'll know a little bit more, but our best guess right now is that when a star is large enough to supernova, that it can have so much mass that although some of it is ejected, some of it actually collapses or implodes down on itself. And that massive implosion creates a hyperstate that's referred to as a black hole. It has so much density and mass that not even light can escape it. Light is sucked into it. And that they exist at virtually the core of every galaxy, including our own. There's a supermassive black hole at the core of our galaxy. I'm going to show you a picture of it soon.
Nothing escaped that.
So, okay, so yeah. Now, two cameras, near infrared and mid infrared. So near cam is this one. It's fairly well focused, and you could basically see one star in the middle. But with the mid infrared, without doubt, there are two stars there. And what they think is happening is that these two stars are orbiting each other and causing ejecta to flow from both of us. So it's like sort of like a sprinkler on a lawn going like this and just spewing out material as these stars disintegrate, forming these massive sort of like structures of gas around them. And these are often called planetary nebula, because in the early days they'd look at it and say, well, that must be a planet, but actually it was just a nebula. The binary hypothesis is that all nebula are stars and element factories, but mostly with two stars in the center of them. This one's particularly interesting because it's relatively close. It's only 2,500 light years away, but it's facing the Earth, you know, straight on, as opposed to from the side. So you get this big, beautiful thing. You can see this through a telescope, and it really is special to see things through a telescope. It really does something to you. It's hard to describe it. All right, let's look a little bit at the instrumentation. There are teams assigned to building these instruments. This is the mid-infrared. And basically, it just takes light and processes the light. It's frankly beyond my understanding exactly how it does it. And it also has a series of filters so that it can sort of pick up different frequencies of light, different wavelengths, and that this can then be fed into the processor to sleuth out various types of information. It's called the MIRI mid-infrared instrument. It's a camera. Then there's the near cam, and that's the near infrared camera. Most of the stuff we see is from the near cam, and it similarly does the same thing. It images things, but it also has a spectrograph built into it, or it's combined with a near spectrograph. And the way a spectrograph works is we collect light from an object and then break it into its various colors. And each color reveals the elements, because if that light, let's just say, is coming from something that has oxygen, oxygen will absorb light at a particular wavelength and leave behind sort of a black line, so that each element has been identified as absorbing a certain amount of light in a certain part of the spectrum. So it's like a fingerprint. And when they get it, they can say, oh, look at the fingerprints. Has carbon, has oxygen, has hydrogen, has da-da-da-da-da. And they can figure out the temperature of it, and the pressure of it, and the velocity of it, all from analyzing the light. Oh my gosh, just from analyzing light. Whoa. Oh. All right. So then you get these pictures that look like this. So that's the near cam, beautiful and spectacular, but the mid-infrared, it's not as focused because it's on a different wavelength altogether, but it picks up a whole different level of information. And so using all these different instruments help us understand it. That's the sun, which NASA put out on Halloween. It's the sun smiling. It's an actual photograph of the sun. And they thought that we would appreciate that. That's your sun. Exactly. All right, so light year, again, is the distance light travels in a year. And yes, light does have a speed, and the distances to things are measured in light years. A galaxy is a gravitationally bound system of stars, stellar remnants, gas, dust, dark matter, which is most of the universe, they tell us, is made of dark matter. And there are like 100 million, 200 million stars in these systems. And as mentioned, you know, there are trillions of galaxies. Now, generally, they sort of look like that. It's sort of visible light. That's what we're used to seeing. But the same galaxy imaged in infrared with the MIRI camera reveals these sort of like cobweb structures. So it's like almost seeing the bones of the particular universe. And the various colors indicate different things. So there's red dots in there, and there's blue. Blue generally refers to new star growth. But then there are other structures in there too that have to be analyzed. And why would it take that shape? So it's a subject of study. Compared side by side, looks something like that. Pretty big difference. Cartwheel galaxy. So here we're looking at the interaction of two galaxies merging together, and there's a supermassive black hole at the core of it. So what you are seeing here, two galaxies impacted, and then they're rippling out like this. The material's like rippling out. And then this other ring out here, which has been moving in that direction and collecting more material as it goes along, is the starbursting, which looks like that. So you can see the activity out here, suggesting that the interaction of the collision between these two objects is manifesting on the periphery. And then the black hole is there. The shape and structure, since it faces the Earth, gives us an opportunity to study these things, because galaxy collisions are very, very common and suggestive of a way that the universe is growing. We don't exactly know how yet. The deep field, which we talked about a little bit, but they'll continue to take these kinds of pictures. These are all preliminary pictures. These are like your first day in Italy, you know, and you go out, and you know, there's the Plaza de something, and you take a few shots. This is the equivalent here. They just took a few shots, and this is what they've come up with. And finding, you know, like a zoo of galaxies, that's how they refer to it, a zoo of galaxies, faint galaxies never been seen before, never. Distant galaxies that have never, ever been seen before. And so everybody was sort of wondering, you know, is this thing gonna work, and blah, blah, blah. And it just didn't work. I mean, it's like a baseball player going to bat and hitting 4 grand slams in one game. It's that good. Now, what we can, yeah?
I wonder if, are they developing software where they can take those streaks of lensed images and reconstitute them?
Yeah. Yeah, absolutely, yes. Yeah, great point. Okay, so what are we going to do with some of this information? So we can now analyze it. So this is sort of like what they do. They identify different parts of the image, and we talked about the micro shutters, so they can actually analyze several things at one time. There's 248,000 micro shutters. And then each one will be analyzed using its spectral information to identify it. Now, what's interesting here, these are, let's see, the top one is 11.1 billion years, that one. But the other ones are older. So this is 12, this is 13, the other one is 13.1. And you can sort of see at one level how they're shifting, but they can identify the actual elements in them by feeding them through the spectrograph. Pretty amazing to, you know, take a picture like this and then say, well, here's what it's made out of. We talked about this slide a little bit, and the example is a good one because many, many, many science teams will be analyzing aspects of what the Webb is going to find. We had great activity for like a high school class to take some new data from the Webb and analyze it. There's no way they're going to be able to analyze everything. It's too much data. So amateurs could go out and start analyzing all kinds of things, and who knows what you're going to find. You know, like some of the smartest people I've ever encountered were in the 8th and 9th grade. If you could actually get them calmed down and seated, you're like with geniuses. Their perceptions are so heightened, and they have brilliant minds. So these people have a lot of potential for discovery. All right, so this one, again, is a galactic analysis using the spectrograph. This is sort of like interesting because on the left-hand side, many of these brighter objects, which are part of the image of the deep field over here, previously could not be seen and have been gravitationally lensed. So you could see here some of these objects are being lensed by these galaxies in the forefront and actually show up in the pictures. So you know all those like oddly shaped tadpole-looking galaxies, well, they're gravitationally lensed. And Einstein helped us understand this by introducing his gravitational theories. And this is a sort of a model of how it works. And I like this one because it shows you down here the warpage of the space-time continuum. So you don't have to imagine it's there. It's distorted by the mass. This is yet another example of the Einstein ring. We talked a little bit about that one already. Here's a more exotic one, and it stretches around like this. So it's a well-recognized form of doing astronomy. Here's several others. And these can be reconstituted. So, you know, nobody really ever thought in 1916 that we could see distant objects using gravity as a telescope, and yet we do. Phantom galaxy. Again, a grand design spiral. And there it is imaged in different types of light. And they're putting these things together. Each one gives us a different bit of information about it. Tarantula Nebula. Some of the hottest and most massive stars known, sparkling in the center here. And yet, when we take another image at a different wavelength, we see something completely different. And then we try to put these things together to gain more insight. Galaxy clusters look something like that. And they're extremely fruitful for not just lensing, but for articulating dynamics between galaxies themselves. We haven't really understood this well. But it can be analyzed. I'm going a little more quickly because I want to leave time for discussion. Wolf-Rayet is super exotic because you just don't see, you know, ring patterns like this. So as the two stars orbit each other, it takes 8 years for them to complete an orbit, and that's a tree ring. So you're seeing about 130 years of growth here as it, you know, spews out this material but has this exotic pattern of orbiting and generating these sort of ripple type of waves and rings around it. And they have identified the material as being carbon-rich, ringed benzene-like structures that are causing these sort of distinct rings somehow. These two stars are like 50 times the mass of the sun. And here's a little image of it. Yeah.
In relationship to that last image?
Yep.
Are they like if you drop a pebble into a pond and waves continue to go up? So that photograph is just taken at one point in time, but those waves are there all the time. Is that, am I thinking of that correctly?
Think in terms of two pebbles dropping in a pond. So I put one twice as heavy as the other one, and I drop them in the middle of a still pond. It'll still ripple, but the interaction of the ripples will cause that exotic pattern. And yes, they just stay stationary. They're actually all sort of moving and expanding, and new waves, new rings are being generated every 8 years.
Like interference?
Yeah, yeah, exactly.
The new waves that are being generated are from the same original dropping of the two stones in the pond, so to speak?
So to speak, but if you think of it as the two kind of stones drop and they actually start moving, like maybe two sticks, you know, drawing something in the water, then you'd get the pattern that you see on the screen. And the gravitational influence of one is sort of drawing the material of the other in a particular direction. And that's to the best of our knowledge how they do it. Different you know, types of cameras taking these, the NearCam and the MIRI, showing, like on the right, you know, that's near infrared. It gives you like a really sharp image of it. This would be great for a science fiction movie. Really great. All right, planets. Ooh, Jupiter. Oh. I mean, It's just so pretty to begin with, you know, and it's got all these moons, but, you know, there's so much to learn about Jupiter. Here's something interesting. If you think of Europa, one of the 4 primary moons that Galileo discovered, it has a subsurface ocean. And the latest estimates is there's more water on the interior of Europa than there is on Earth. And so there's a mission going up there. They're going to land, use sort of like a heated probe to go through the ice surface and then try to explore the ocean underneath. They're looking for volunteers if you want to go. And then, of course, Io is volcanic. Now, Jupiter orbits on its axis about every 10 hours or so, 12 hours, something like that. So it's spinning around, and then all the systems of moons are too, and the gravity is so intense, it's like sort of like bending and stressing these moons, and they're hot. So it's freezing out there, sub-freezing, but it's intensely hot and has generated all kinds of curious effects, which we're trying to discover. So the rings, the auroras, diffraction of the auroras, it's got all these moons out there. And so we're trying to image all this and figure out, you know, how it works. Now here, it's sort of a slightly better image where this is in mid-infrared, so it's picking up a little bit more of the contour and shape of the various bands. Now these bands don't all go in the same way, so this one might be going this way, and then that one's going that way, and then this one's going this way, and then you have the big red spot here, which is, for as long as we've been observing Jupiter, that's been spinning around, and then the auroras. So it's one of those things, you know, it's like, say you start to study something, you say, oh, I understand this subject. Then you study it and you go, oh yeah, I didn't think of that, I didn't think of that, I didn't think of the other thing. And then you realize, wait a minute, the goal that I'm pursuing is getting higher the more I study it, the more I try to contemplate it. What's happening here? What's happening is called learning. You start off thinking you know something, and then you find out that you don't. And then you can actually start to learn what's really there.
So Russ,
Yeah.
about these pictures,
Yeah.
understand that they're being taken with different technology, as
Yeah.
you described very clearly.
Yeah.
But aren't they also, so that you take an infrared picture, you see different structures, but then the coloring is something that gets added afterward.
Correct.
We're not actually, the photograph is not actually sensing that color, it's being added after. Right?
It's being added based on the frequency and density that's being perceived. So they take the image and then they take it with different lenses that detect different things. And you can kind of cipher out how dense something is or what's there, and then assign a color to that. Now, the colors being assigned are arbitrary, but the data that it's based on isn't. So whether it's colored blue or green or something like that is arbitrary. But the patterns that you see are the same patterns.
Yeah.
So it's artificially colorized to look more dramatic to us?
To reflect what we can't see in the infrared spectrum. Yeah. There are animals, you know, that can see in infrared, right? People are always wondering, oh, can animals see at night? Animals are all out at night. What do you think? They just like walk around going, oh, I hope I don't hit a tree or something. They can see in infrared, many of them. And they've actually detected sensors in a lot of them.
Do they try to base the colors on the frequency that is really there though? So it's kind
They
of
try to match it up, yeah, as best we can. Okay, well, you know, there's more to go, but it might be more fair to just open it up to discussion and questions. What kind of, yeah?
One of the things that we've seen on physicists who are analyzing the deep field images
Right?
is they expected to see galaxies that were immature. When you're looking that deep
Yeah.
towards the, at least the beginning of the visible universe,
Yeah.
you would think you would see less mature, less big, less sophisticated galaxies. But instead, they're seeing just as complicated, just as large, just as mature galaxies as they see anywhere else.
Yeah.
And that is throwing into question the fundamental conception about the Big Bang. And I just wonder if you could talk about that a little bit.
Yeah, so we're trying to look all the way back to the origins of when galaxies and stars started to form, to try to figure out what are the dynamics that make this happen from seemingly nothing. Now, granted, it's a little bit like saying, I want to know how a watch works, so I'll throw it against the wall, and then it'll break open, and then I'll see stuff in there. And then I'm going to figure it out. That's how the Large Hadron Collider basically sort of works, tries to discern patterns. But we have seen a lot of these original galaxies, but there's so many of them. Like in the deep field image, there's more galaxies there than we'll be able to analyze in the next 50 years. That's how much information we've got back from just one image. So we have to kind of figure out, okay, now AI is really going to help on this, because if as we start to learn things about it, we can sort of process using AI computers that will go through, images and information several million times faster than a human could. And we can direct it to find patterns. And it is going to be beyond spectacular. So our friend Daniel, in fact, he's an aspiring astronomer specializing in AI. So I fully expect to see him in Scientific American soon. Well, relatively soon. So it seems like we go into it with the mindset, and then in every instance, the mindset is sort of blown up. It's like, no, it's bigger than that. It's more sophisticated than that. What's that? Yeah, it always is. But I don't know, we have a tendency to want to have this gravity of our conceptions take shape. The problem is we start to see it that way. And then that becomes a reality for us, but it's not necessarily the reality. So they seem like they're getting a lot more open-minded.
We want to take a question from the internet,
Okay.
from Marlon.
Okay.
So get ready, because it's obscure.
Excellent. We have to love it.
He says, infrared is beyond red. Ultraviolet is beyond violet. Yet violet is a combination of blue and red. Does this suggest a periodicity of nothingness to somethingness to nothingness?
I'll just say yes. So read it again. Hi, Marlon.
Oh, God. Yeah, it's hard. Infrared is beyond red, ultraviolet is beyond violet, yet violet is a combination of blue and red. Yeah, well, does this suggest a periodicity of nothingness to somethingness to nothingness?
So you all heard the question. Now, it's a little bit different because mixing colors isn't exactly like the frequencies on the electromagnetic scale. It's a little bit different, but the analogy holds. So it depends what you say, what you think of as something and nothing. So things we can't see could be considered nothing in relation to what we can see, which is something. That sort of makes sense. But that doesn't mean nothing is nothing in relation to something else, which is even more subtle than that. And then there's something more subtle than that. So it's like the Wolf-Rayet rings. One level of meaning is gross in relation to the next, is gross to the relation to the next. So we would point to the idea not a once and for all, like written in stone law, but a process by which we unfold knowledge by being more open, making experiments, and being daring to think differently. Thanks, Marlon.
Is the incomparance of direct light to additive light? So like when you mix colors, all the colors would be black, but all the light would be white.
It's a different context. You know, like you don't want your dentist to be an artist and say, this works when I was, is it a thought? Yeah.
Sorry, go ahead, I just lost my train of thought, but
We'll come right back to you. Yeah.
Now, when we think about you said, I thought black holes were at the basis of a lot of the galaxies, and yet you said they were kind of like the offshoot of a massive red thing. So anyway, what kind of, two things. One, why is the black hole at the center of galaxies if it's not sort of the origin of the galaxy? And also, if they're studying it, what are they studying it that if nothing comes out of it?
Well, let me show you, first of all, the black hole at the center of our galaxy. So we've actually managed now, this isn't from the Webb, this is from, once the Webb images this, nobody's going out of their house for a week. You're just gonna stare at the screen. It's like, but this is the best that we have now. This is a supermassive black hole, has a mass 4 million times greater than our sun. 4 million. And the scientists that kind of pulled all this together won the Nobel Prize in 2020 for it. Now, how do we get black holes? And where do they come from? And how they manifested? We don't entirely know, but from what we think, the big red thing that you're referring to was a supernova. So when there's a supernova, one of the largest, explosions in the universe, not all the material necessarily explodes. It can kind of go and collapse back down on itself because of the amount of mass. And then, they think there's all kinds of theories, but some say it's like the size of the trillionth of the head of a pin. So it goes back to like the original Big Bang, but that we see the effects. So what we see on the screen is the material around the black hole. You can't see a black hole. And we're so interested in these colliding galaxies and so forth, so we can say, well, how are they formed? Oh my gosh. And this is the best that we can do right now. Now, having said that, if you don't read Scientific American, please start. It's a very readable magazine now. It used to be kind of science-y. Now they've realized most people just want to know something about science. There's the September issue, which I'm sure Robert enjoyed, Black Hole Mysteries Solved. Several articles on black holes. Oh, I mean, it's a page turner. I mean it. It's really something. If you have Apple News, or you can get all these things online now, and you can read this, it's enlightening. Should we ask another question, or are we there?
Well, because we're streaming and there are limits and we've reached 4 o'clock, you can answer this question later.
Okay.
But I encourage everyone to stay because we're going to have someone give the vote of thanks in a few minutes. And it's always nice to hear that impression. It kind of wraps up the evening. But I want to alert everyone to our next program first, Boundless Mind, in 2 weeks on November 19th. New Paradigms of Consciousness. Wow. What is the nature of consciousness? Now this is a must, right? We're going to find out what the nature of consciousness is. It fits right into the cosmos. So it will things like precognition, prophetic dreams and visions, mystical insights, adolescent genius, intuitional breakthroughs. So there'll be a lot of interesting subjects addressed.
Yeah.
So we encourage you to participate in that. And we also want to thank you all for your participation here and on the internet. And just remind everybody that we are solely a volunteer, associated by voluntary efforts and time, money, and effort. And I don't think there's any organization in the world that's more volunteer than the Institute of World Culture. It's all based on that. There's a donation box at the back of the room. Anybody that wants information can email Carolyn at worldculture.org or Jerry at worldculture.org. So now I would like to invite Joe Miller up. Come up to the mic if you will, Joe, so everyone can hear.
Thank you, Robert.
All right. Well, it is my good pleasure to offer the vote of thanks this afternoon to Russ Lewin for this extraordinary introduction to the Webb telescope. I think, you know, there was a puzzle in there. He was talking about the problems with depth perception, and he gave an upward visual of juggling hands and said, see, it's hard to tell which balls are farthest away. It actually wasn't so hard, because the farther away ones were being reached for by hands, I noticed. And I wondered if that might be the case, if when the Webb's resolution gets a little better, if those faraway galaxies might be reached for by hands. That we'll have to find that out. This forum today seemed to be about the outward universe, but I think what I'll walk away with is that it's really about the smallness of mind to encompass what's really going on. It's just, it is so vast, and that it really shows how, I mean, can you even imagine a galaxy even, let alone trillions of galaxies of galaxies. But I want to thank Russ Lewin for cutting through the dust. He used his, got us all onto infrared, and so we got a real clear view of what the Webb is all about, and his incredible awe for the engineers, and it really should be. It's awesome. You know, there's this old concept that man is the mirror of the microcosm, the microcosm of the macrocosm, and you know, all of us are mirroring what it means to be in the universe and what the universe is to us. All of us do that, whether we're aware of it or not. But to think of these people who do it so consciously and have carried the torch of precise science and material science forward to such a degree that they can do something like this, it's so awe-inspiring. If Newton could come back and say, wow, way to go, you guys, you know, it would just be incredible. So with that in mind, thank you very much. Let's all offer a vote of applause to Russell.
Thank you. Do you want to answer a few more questions or not?
Sure. Anybody
Because
who's...
Joe kept raising his hand. What's your question?
Oh, you know, a really basic question. The structure of the telescope has the hexagons of mirrors and then a tower in the middle. Yeah. And I think you might have made a passing reference to another mirror, which we haven't seen. Is it true that those mirrors go into shine onto another mirror above the tower and then that image?
Exactly right. Yeah.
Okay.
Yeah, so there's a secondary mirror that focuses all of the 18 hexagons. And they're pointed at the secondary mirror, which collects that light and focuses it, and then sends it into the instrument chamber, where that light is analyzed, and then the data is sent back to headquarters.
Now, do we dare ask, is there a problem with the cracks between the hexagons?
No.
They don't distort the image in any way, or?
No. You remember back when the Hubble was launched, there was a distortion, and they had to go up and do a big thing. So they've, you know, the reason it took so long to make it, they wanted to be perfect. And that was smart. You know, the old saying, fools rush in where dangers fear to tread. Take your time and build it right and build it well. It's sort of like a way of living, really. You know, to do something right requires attention and time and care, craftsmanship, you know, and they truly exemplified this because once they launched it, there was nothing that they could do, you know, to correct it. So far, it's worked well. They used beryllium for the backs of the mirrors and coated them with gold. So they're very, very, very robust. Now, it's possible, you know, there are little like rocks and stuff floating around out there. If by chance they bump into one of the mirrors, we don't know. That could happen.
But the others could operate independently if need
They
be.
could,
Yeah.
yeah. But this particular telescope, you know, most of them are in a tube. So if it hits the tube, that's okay. This is just sitting out there.
Yeah.
You know, it's just exposed to the universe, and there's nothing between it and the light that it's collecting. So I sort of, you know, it's like 100% faith type of a situation. And so far, you know, it's worked just beautifully. They haven't released, I think they've released maybe 20, 25 images so far. So they're being very careful, you know, and so when an image comes in, they subject it to peer study before they say anything about it. That takes weeks, maybe even months. And then they release it as valid science, but they don't just say, oh, look, great picture, you know, look at this. So they've kind of peeled that back. Plus, I mean, we're at a state now where you can see online exactly what they're coming up with every single day. Just Google it. And I can remember the days of the Voyager. I would drive to Pasadena, and the shots would come into an auditorium, and they'd show it on a big screen, and all the space nerds were there, and you couldn't hear yourself think. There was so much uproarious enthusiasm for these shots coming in from space, and they'd come in line by line, like, and then people would just be going wild.
Like a touchdown for your team.
Oh, except better. I mean, with science nerd heaven. Now you just get the picture. Donna. Oh, sorry. Kim? Yeah.
Well, Johnson and Donna have a question.
No.
Go ahead, Kim.
If you look at the evolution of the universe as a whole over a very long period of time, you see more evolution of metallicity in the stars rather than just hydrogen. Like that, what was it, Reina, I forget, the one with the period, the waves going
WR 140.
Yeah, that were very carboniferous. What does that imply for the future of star evolution? Like if, you know, this one mass of mostly carbon was to be a nebula that became a solar system.
Yeah.
You know, and then eventually higher and higher metals. What does that imply?
So that's a great question. What does it imply to say that, you know, there's all these heavy metals that are being generated by the stars? Well, the implication seems to be, will it generate different types of structures or what? And one of the big areas of research is in exoplanets. And one of the most interesting one is called TRAPPIST-1. So it's a star, but it's got 7 moons, sort of the same distance as the Earth is from the sun. So they call that the Goldilocks zone. And so they're sort of analyzing it to see if indeed there might be some either hope for or perhaps is life on it. One of the big questions is there other life in the universe? It's hard to believe that we're it. I mean, truly, I mean, most of us would say that. But probably most scientists don't draw the conclusion, therefore extraterrestrials are flying around Area 51. Maybe they are, or maybe they're not, or maybe there's other dimensions, but the big question is there life out there? And we haven't found anything yet. Even on Mars, we haven't found any form of life, not even a fossilized microbe or anything like that. So I think this whole metal thing suggests that there's an evolution in the universe towards some life form of some sort, potentially, but unverified as yet. That's our best guess, but maybe someone else has some ideas in relation. It's the big question. I think there's life on everywhere, but you can't see it. But scientists don't really appreciate that view.
Well, mine's not great. I heard at some point that the folding of the telescope, I think I heard this, had some origin in origami.
Yeah.
I was wondering if you knew anything about that in relationship to this one.
Yeah, that's actually an area I'm really interested in. There's a whole branch of science that's using origami to make spacecraft that are light and flexible and easy to make so that you could send them out. You could send all kinds of them out to places like the moon or Mars, and they're like flexible toys with wheels and lightweight computers on them so that they could navigate around, and that you could take really large structures and fold them origami-like, put them in a payload, and then send them to someplace like the moon, and then unfold them as structures. Very, very interesting area of development, and one that's really being capitalized. There are branches of, like at JPL or different space places where they have people researching that. Because you save weight, you don't have to make things that are very complicated. You can send them places easily, and they're inexpensive. So it meets all the big criteria for making spacecraft. Because, if this took 30 years to build and cost $10 billion, what if you could make something in origami in 6 weeks and do a similar function? Not that it could be like the web, but something else. So origami is a huge area of research. So thanks for bringing that up.
And you wonder if there aren't some fundamental mathematics involved.
Oh, yeah.
That could be expanded on and that we don't know anything about that could actually apply in
Yeah.
all kinds of different ways.
Well, this is the thing, if you can get involved in puzzles or geometry or problem solving, and you like it, you actually like it. That's the kind of person who does that kind of thing, where it's real patient, like you work on a problem for a couple of weeks. Now, some might say, oh, just go to the store and buy something. No. I want to figure this out. I want to figure out how this works, and then I want to make something, and it adds a dimension to how you think about things. And as we get into a mechanized society, people can't do anything. So I asked my colleagues once, what are you going to do this weekend? And he said, I'm going to fix my water heater. I said, hey, I have a lot of tools. I'll help you if you need it. He laughed and said, no. I don't fix it. I call somebody on my cell phone to fix it. I'm like, well, that's not problem solving. And he laughed and laughed and laughed. And then he goes, what kind of tools do you have? And he laughed even more. But I like putting in water heaters because of the process and the appreciation and what it is. And you have to understand the laws of nature. And it's a whole way of being, So it's sort of like work as evolution. You not only learn how to do things, but you master yourself by doing it. Like gardening is that way too. Robert, you're the master of ceremonies. Other questions?
I don't know, Jonathan and Diane have questions?
Diane?
You have a question, Diane?
Really simple question. How much international cooperation went into this?
A lot. So there were thousands and thousands and thousands of people. So the Europeans have organized similar to NASA, they call it the European Space Association or Organization. People from, the Netherlands and France and England and Spain have all bonded together. And as I understand it, they speak either English or French there. Those are the two languages they entertain. And they are very, very developed and very sophisticated in their efforts. The Large Hadron Collider, is in France. The Canadians were a big part of this. The Russian scientists, all scientists get along. They don't care about what country that you're from. They're way beyond that. But the Russians, not so much. I hesitate to say why, because I don't know, but not so much. Eastern Europeans, to some degree, Japanese, to some degree. So it was definitely an international effort.
Just because the Russians and Chinese really have brilliant scientists.
Oh, yeah. Yeah, Russians, at one point, it's like 50% of Russian males were called engineers of one sort or another. That's just what they did. But I once worked someplace where we were corresponding, was a software company, corresponding with Russia, and they sent us something in an envelope, and they had a paperclip that we couldn't actually figure out how it worked. It was a very complicated paperclip. And we spent hours and hours and hours like, okay, here's the stuff, we'll read that later. What about this paperclip? That is really something. And we laughed and laughed. Just a way of thinking, different way of thinking, but so what? But the Russians have brilliant people, not just science, but in the arts and in literature. Absolutely fantastic. So I've always been a fan of Russia in many respects. Other thoughts? Dan?
Well, there are two questions. One is connected to life. And from what I've been hearing about scientists, because you mentioned water in different planets, and they seem to be saying that if they can find water everywhere, then life is everywhere. And they seem to be trending that way because they're finding water and water. That's what your impression.
Okay.
The second one is, you mentioned what anyway, the point is from the black hole expansion, and you mentioned about Hubble's law or something like that structure. We were thinking about the process of from the black hole, things differentiating.
Okay.
Is there a view that from the black hole you have this expansion and then contraction, and then from that point again you have another expansion, and at this point you get more and more differentiation and all this. Anyway, I wonder.
It's a great question. As far as black holes go, we just know almost nothing. Almost nothing. And that's one of the great hopes, is that the Webb will start imaging and we'll start to try to figure out something about it. But our ideas of it is very crude, and it's quite obvious that there are dimensions to nature that are extremely powerful, but defy every law of physics that we understand. We do not understand it at all. Does it have some kind of special energy? Is that where dark energy comes from? Is it dimension? Is it a hyperdimension? We don't know. But it's probably not what we think, whatever that is. So we don't know. But as far as life goes, the question is, we look for life as we understand it, carbon-based life. But what if there's life that doesn't obey those particular laws? What if it's on a different dimension? So you could be on Mars, maybe, looking around for life, but you can't see the dimension on which it truly exists. So we say, okay, let's dig deeper. Okay, but it's not, that's the same dimension. It's still digging deeper. You have to look on a different dimension. How? Just like a black hole. Who knows how? We have not evolved even close to the idea of knowing how to do that.
Yeah, but we're going to explore that in a couple of weeks.
Yes, in a couple of weeks, we're going to explore consciousness. And that probably is our best spaceship
Yes.
for exploration.
Yeah.
Well, thanks, everybody.
Well, thank you.
Appreciate it. That was fun.
Anyplace else in the universe. Presentation. Thank you, Russ.
Thank you. Thank you. Thank you. Go universe.
Thank you, thank you. Looking at something so big that make us forget something so